the 2023 PhysiCell Virtual Workshop and Hackathon. This session, we're going to talk about signals, behaviors, and a modeling grammar in PhysiCell that's going to be the basis of our work as we build models through the rest of the week. And so our session goals here, first of all, to think about how we kind of frame mentally cells as signal processors and learn about the available signals and behaviors in the PhysiCell modeling platform, and learn about how we can connect these signals and behaviors into a grammar to start describing our biological hypotheses and turning these into model rules. And this will set the stage to prepare us for rules-based modeling in PhysiCell, which we just introduced this past year, and we'll get into in the next session. So I just want to remind you that if you have questions during the session, please go ahead and write them into the chat window, and we will make periodic pauses just to stop and see if anybody has questions and try to address those. And some questions, to the extent that we can be, will be answered by typing by other members of the lab in the chat window. So this is a bit of a review from some of the earlier asynchronous materials, but I think it's a really helpful way to help us get in the right frame of mind for thinking about cells and agent-based models. You know, that in cancer ecosystems and in other multicellular systems, we're very interested in how individual cell behaviors, a limited palette really of individual behaviors like growth and division, differentiation or changing cell type, death, consumption of things in their environment, and metabolizing them, secreting things into the environment, interior signaling, mutations is another kind of type change, or motility or migration. So you have some, a handful of individual cell behaviors, and then you have some more cell-cell interactions, things like adhesion, sticking to other cells, or mechanics, pushing each other around and resisting deformation, predation, where cells can actually eat one another or consume one another or attack other cells as another form of interaction, and more generalized contact interactions. So you go from this palette of single cell behaviors and pairwise interactions, and you put this into an environment with physical constraints like diffusion limits. If I secrete a signal over here, it has to diffuse through the environment and reach a cell somewhere else, and that signal attenuates. It gets harder and harder to detect. Oxygen and glucose and growth factors must be released by some source and reach other cells by diffusion. So these become limits on behaviors and communication. And then, of course, there are mechanical limits like mechanical barriers, or in the case of cell motility, you may need extracellular matrix to actually get traction to move. And so if you have matrix density differences, that can become a physical constraint. And somehow we put these together and you get a bunch of cells with their individual behaviors and their individual pairwise interactions and their physical constraints, and you put this together in a big system and get an emergent ecosystem. And in cancer, that ecosystem tends to be dysregulated. In tissues, we hope it is regulated. And we want to understand how we get back and forth between these. And in particular, we want to understand how the rules of individual behaviors and interactions put into this large ecosystem leads to the emergent behavior of the ecosystem, of the tissue, of the cancer, of the tumor, or of the disease. And of course, as multicellular systems engineers, we want to control these systems. So as any scientist, we use models to detangle these complex systems, and we're using agent-based models as our virtual laboratory, in our particular case, PhysiCell as our virtual laboratory. So to kind of help us frame this as a conceptual model, I want to think a bit about signals and response in terms of communication as our conceptual framing, that we can really think about a lot of these interactions as an interaction between a sender and a recipient. That a sender sends out some signal and a recipient responds. And so in our context here, a signal is any stimulus that can elicit a behavioral response. Those signals can be a broad variety of things. They could be chemical signals. They could be contact with other cells. They can be their own status, like am I dead or alive, or where am I in the cell cycle? They can be pressure or mechanical signals. And so these are signals that can be released into the environment, and then a recipient will have a behavioral response, for example, changes in cycling or death or motility or secretion. And sometimes the sender and the recipient can be the same individual. So you can send a signal out to yourself in this kind of a framing. Typical examples is, say, a macrophage. The sender can secrete IL-6, that's their signal, that drives chemotaxis, that's a behavioral response, in CD8 effector T cells, and that would be the recipient. So we have a sender, a recipient, a signal, and a behavioral response. Or another example, an epithelial cell, the sender, exerts pressure, that's our signal, that decreases cycle entry, that's a behavioral response, in another epithelial cell, and that'd be the recipient. So sender, recipient, signal, pressure, behavioral response, cycle entry, right? So thinking about these as who sends a signal, who receives it, and what do they do with it really becomes a good framing for these kinds of systems. And so agent-based models are a great way to kind of start putting this into a neat and tidy thing that we can get our heads around. The individual cells can sample the signals in their environment, be they things like secretive factors or other things in the environment, pressure gradients, and then they can behave individually with a behavioral response. Actually, this is a signal that I was hoping for, the slide I was looking for. So you can respond to things like chemical gradients, process them through your rules, and they'll say, as a function of these signals, I change my behaviors in the following ways. That's a system of rules, which really codify our biological hypotheses, that we have something we've observed with a domain expert or through an experiment or through reading the literature. And we say, oxygen tends to increase cell cycling. Well, that's for us is one statement, one biological hypothesis that becomes a rule. Or you might say doxorubicin increases apoptosis. Well, that's a hypothesis based upon observations that we can codify as an agent rule. And so agent rules are very, very closely tied to biological hypotheses and really becomes a way to systemize what we think a particular type of cell does in terms of saying, when I see these signals, I behave in the following way. And so that's really the framing that we'd like to go with for the rest of the week. So traditionally, these agent rules are written as handwritten C++, one at a time. And a lot of people write these out as big flow diagrams, which is really nice. But in biology, a lot of processes actually happen in parallel, not sequentially. It's not like, if this, then that, if this, then that. It's kind of everything tries to do its own thing independently with some cross feedbacks. And the problem with these kinds of flow diagrams is that as the complexity grows, as you add more biological rules, it gets harder and harder to decide where to insert a new rule into this mess of a framework of this diagram without breaking your other rules. And the placement of the rules makes a big difference on the behavior of your model. And we would hope that adding new hypotheses doesn't break old hypotheses, but instead just makes them better. And so that is an interesting thing to think about. The other problem, of course, about handwritten models is that it gets very difficult to maintain them as the complexity grows, and fewer people in your collaboration understand what's going on, which makes it hard to maintain and sustain projects and collaborations. And it also discourages participation by multidisciplinary participants. We'd like biologists and clinicians to directly write model rules. We would like them to work with mathematicians in real time to see how they go, rather than saying, well, here are hypotheses. Now you have to go hand write them. So everyone, away you go for a couple of weeks or months, and then come back and see how it goes. That really kind of discourages good interdisciplinary work. So we're trying to get away from that. And so our goal that we hope we've reached, and that we'll present here in the modeling workshop, is to create a modeling grammar that helps address these problems. It needs to be human readable or interpretable as plain English statements. Something that makes it really easy for a domain expert to actually write out a hypothesis once they're used to thinking in this way. But it needs to be not only human readable, but also computer readable. So it has to be able to translate it into a standard mathematical form, and then from there generate code. And it needs to be able to integrate new knowledge with prior knowledge. So if I add a new rule, it can't break an old rule. And there have to be multiple ways you can build rules, either hand writing rules by domain expertise, or maybe data-driven modeling and other workflows. So the key elements we need for this kind of grammar is, first of all, any grammar first requires a vocabulary. And so we have a dictionary of cell processes or behaviors that have standardized reference implementations in PhysiCell. So you download PhysiCell, most of these behaviors already work out of the box. You don't have to handwrite your own model for cell division. You don't have to handwrite your own model for cell migration. What you do write is a model for how quickly a cell divides, or how quickly a cell migrates, or whether it migrates parallel to a chemical factor or a gradient. So we want you to think more about modeling how fast processes happen, rather than modeling the fundamental processes, which can be very difficult to build and require a lot of redundant work. So we have a dictionary of standardized implemented cell behaviors, and we have a dictionary of signals that cells can easily sample in their environment. And then, so if you have those two things, then the next thing you need is a grammar or a language to connect them, to say this signal increases or decreases that behavior. And then the last thing you need is a way to map those grammatical statements onto mathematics and code. And that's the last bit that we'll be presenting here today. Okay, so are there any questions on this before we keep going? Okay, cool. So let's talk, so I'm going to go into kind of an intermediate level of detail to talk about the reference cell behavior models that are available out of the box in PhysiCell as of the current version. And these are going to be our building blocks for building grammatical statements, these cell behavior hypotheses, and building models. And so first, kind of the high level view that based upon reading a lot of people's great models, including a lot of great models by people in this room, we have found a lot of processes that we could start to standardize, saying, these are recurring themes with fairly similar implementations across modeling platforms that we can kind of get our teeth into and write down in a simplified form. So things like cycling and death processes, we were able to write out very nicely. Transport processes like secretion and uptake of chemical factors and diffusion equations. Migration and chemotaxis as biased random walks. Mechanics and adhesion by two formulations, either by interaction potentials or by basically linked springs. Transformation, or cells changing from one type to another. Fusion, phagocytosis or predation, effector attack, and then some custom symbols. And each of these standardized models will have their individual parameters that we can uniquely match to symbols in our language. And so to get a little bit, intermediate level of detail, the first thing we implemented a long time ago was a series of reference models for cycling with varying levels of detail. And we can get into those as we go later. But the idea is that a cell cycle is essentially a cyclic graph of connected phases. G0, G1, which is phase 0 in this model, goes to phase 1, which is S phase, then to G2, then to M, and then two cells divide and go back to phase 0. So in our nomenclature, the 0th phase is always the entry point of the cycle, and the last phase is the phase right before division. And so the key parameters, among other things in this model, is the rate of exiting one phase to go to the next phase. And by convention, exiting the 0th phase is cycle entry. And so a lot of our hypotheses really get down to how quickly does cells cycle? That is, how often do they enter the cycle or leave the 0th phase, this resting phase as it may be. And so in mathematics, we have, kind of a probability saying that if I have a transition rate between two phases and a delta t chunk of time, that gives me a probability of that cell progressing from one cycle phase to the next. And so most of the models are already built into that low level, and we can focus more on modulating how we progress through this cycle. And so the key parameters are the cycle entry rates, the overall cycle entry rate, this one transition, or generally the exit rate from any of the phases in our model. We also have some reference behavioral models for death. And while there are a bewildering variety of ways that cells can die, we have kind of, for now, broken it down to two prototypical or stereotypical types of death. We have apoptosis as kind of the prototypical non-inflammatory programmed cell death, and necrosis is our typical uncontrolled inflammatory death. So the idea is that apoptosis is all controlled, that the cells are going to shrink and then eventually get removed from the simulation. And so the key parameter here is just to say, what is my apoptotic death rate? If I have a live cell, what is the rate of it becoming apoptotic? And so if you then multiply that death rate times the delta t, that says that in some small chunk of time, that's my probability of entering the apoptotic cascade. And then from there, we have a built-in model that can kind of finish the job. And so remember too, that death is not an instantaneous thing, it's beginning of a process. So becoming apoptotic is the event that we want to think about here, and then let the model run out and go through its course. Likewise, necrosis, we model as the cell first swelling and then bursting and then shrinking very, very slowly over time. And unlike apoptosis, that's an uncontrolled process and it goes much longer. Here, the key parameter is just the necrotic death rate. How quickly or how frequently does the cell want to enter that necrotic cascade? And then the built-in model finishes it from there. Other reference models that are important is cell, basically biological transport. And so we have a series of partial differential equations that are solved in PhysiCell. And for each one of these, we have diffusion. Do you guys see my mouse pointer? Hopefully it's circling this term over here, the diffusion term.
Yes.
Okay, that's a relief. So we have diffusion and decay. And then centered at the cell's locations, you can have secretion. So that's like a source term. You have uptake, which is our consumption. And then if these particular terms are not general purpose enough, you can have control over net export term. And so this gives you a lot of control to have cell-based sources and sinks, and then diffusion into the environment. And so the key controllable parameters are for each diffusible substrate in your simulation, you can control the secretion rate, that's this source term over here. The secretion target, this is the target it's trying to reach when it secretes this diffusible factor. The uptake rate, and then the net export rate. So these are the 4 parameters you can control for every individual cell, for every individual diffusible substrate. Migration, very important. And so we model migration as a biased random walk, that a cell will move for some amount of time, let's say based upon its persistence time along a path, and then change direction and move again. So the amount of time it goes in one direction is based upon its persistence time. So go persistence time on average, stop, resample, choose a new direction. Now, the next question is, how do you choose that direction? And so we have a migration direction or motility direction. And in Brownian motion, you just pick a random number and your bias is 0. And so you end up without this first term and only this random variable here. And so your migration direction is completely random in the unit sphere. At any time. So basically you migrate a little bit, pick a completely random direction, migrate a little bit, pick a random direction and keep going. And so that would be classical Brownian motion. But if you add a bias to it, you say that there's some direction that I want to go, then you can have a biased Brownian motion. And so if your bias, first of all, let's go to the extreme that the bias parameter or B is 1, then the random term is gone and your direction of motility is just completely along deterministically along this bias direction. And so, for example, that bias direction could be a chemical gradient, or it could just be an up arrow. And so you put these two together, say, okay, I migrate for a little bit, I choose a new direction. My new direction is some combination of randomness for Brownian component plus my bias direction, and that'll be my new direction, and I travel, and then I choose a new direction. And so on the whole, on average, your motility will be along that bias direction, but the individual paths can be very random. And so that gives you a biased random Brownian motion, the key parameters being the migration speed, how quickly you move along this path, the linear speed, the persistence time of how often you change direction, and then the bias of saying how much do I follow that intended direction of travel, the bias direction. And so chemotaxis is just a particular form of Brownian migration, of biased random migration, that we pick the bias direction here to be some weighted sum of the chemical gradients. And so in classical chemotaxis, only one of these terms will be non-zero. But generally speaking, we now model it as a weighted sum. And so if your parameter or your weight is a positive number, then you're going to go towards that gradient. And if your weight is a negative sign, then you're going to go away from the gradient. And by choosing the relative values of the weights, that lets you choose prioritizations for the cell migration that they want to, let's say that one term has a weight of 10 and the next term has a weight of 1. That means that it's going to take really be more likely to go along the weighted 10 gradient than it is the weighted 1 gradient. And so this allows you to kind of set prioritizations if they're listening to multiple chemical cues in the environment. And so that is a modulatable behavior. Okay, the next thing we have, so I'm sorry, this is going to feel a little detailed, but hopefully this gives some framing as we get into the rest of the modeling. So the next thing we have is cell adhesion, which we have classically modeled as adhesion potentials. That says that two cells that are within interaction distance, like these two over here, can exert basically a potential that says that you're going to go towards the center of mass between the two. So there's an attractive force. It's just like magnetism, basically. You almost have like an inverse square law. But here we just say that two cells that are within interaction distance, if they're both adherent, are going to have an attractive force to one another. So cell J is going to move towards cell I will move towards cell J in an equal and opposite attraction. And to model some of the extra finesse of biology, we model this a little bit more to say that cell I has an adhesive affinity to cells of type J. So you might have a cell that sticks really well to one type and very poorly to another type. And so let's suppose that cell I over here sticks very well to cell J. It might have an adhesive affinity of 1. Whereas it might have a very poor affinity to this guy over here and have an affinity of 0.1. So this adhesion would be stronger than this one over here. And so those are kind of the main priorities here. The other thing is that cells can only stretch a finite distance to form adhesions. And so we give the cells a relative max adhesion distance, which is a relative to the cell radius. It's a factor of the cell radius, a multiplier. So by default, it's usually 1.25, I think, if this is a cell. I would probably pick 1.5 if I were to default that today. But that's one of the controllable parameters is your adhesive affinity to the different types of cells. By default, we'll just give them all the same affinity of 1, but you can change that. You can change the strength of your adhesion. We give a default parameter that gives some kind of a reasonable cell adhesion, but you might want to increase or decrease that parameter to make a cell more or less adherent. And you can also change how stretchy the cells are, in effect, by saying how far can they stretch to form an adhesion. On the other side, now, there's actually a more advanced form of adhesion that we more recently introduced, that cells can actually form more persistent spring adhesions to other cells, which gets a little bit more realistic. The problem with adhesion potentials is that it's just as easy to form an adhesion as to break. So it models loose adhesion of cancer cells pretty well, but it doesn't get more coherent adhesions of things like epithelial tissues. So for this, you might want to use spring adhesions. And the idea is that every cell can have a maximum number of spring adhesion links it can form. In 2D, 6 might be a good number for that, for like a regular hexagonal packing. In 3D, 12 might be a good number for that. The idea is that you have, as long as you have less than your maximum number of adhesions, you can check for things in your neighborhood, and you have basically an attachment rate saying, I have a probability of forming an adhesion to this other cell over here based upon my likelihood of adhering to it, its likelihood of adhering to me, the delta T, and things like this. And so the higher your attachment rate of my cell and the other cell, and the higher of our affinities to the others, actually, sorry, it's the other way around. The higher my attachment rate and the higher my affinity to that other cell type, the more likely I am to form an adhesive bond to that other cell in any chunk of time, delta T. And so if we add it to my list of adhered cells, that counts towards my maximum number, and we go from there. The other thing is that cells can stochastically detach themselves. So they can go through their list of current links and say, what's my probability of breaking this link? And right now we just say, well, that's my detachment rate times delta T, and I just keep applying that to all of my links, and the cells can attach and detach. So this allows you to kind of set things like attachment lifetimes. You can imagine forming hypotheses that say that some cells in some conditions may reduce that lifetime or increase the detachment rate in certain conditions. And so that's something that's very possible. And lastly, we say that the strength of the adhesion combines both the adhesion affinities of the two cells, so that how well do they stick to one another, and their relative adhesion parameters, in this case, an elastic spring-like constant. And so that's how we model a more persistent type of adhesion. On the flip side, cells don't like to occupy the same space at the same time, like any physical object. And so there is a repulsive force modeled, in our case, as another repulsion potential. And so we model these all together. Okay, so now we're getting into some of the more biological behaviors, less physical, and that any cell can change into another type at any time. And so basically, for every cell, you have a vector of transformation rates, one for every other type of cell. And so at any time, based upon your transition rate, your transformation rate, cell type I could turn into cell type J based upon its transition rate times the length of time you're talking about. And so basically, your controllable parameters for these behaviors are these transformation rates. Another reference model that's built in, mostly we got this from some viral biology and also muscular biology, is that cells can fuse together. And so you can have cell I and cell J. If they have a high fusion probability or fusion rate, they can fuse together and form one multinucleate cell. And so what we'll do is we will combine their volumes. We will recenter their position at the center of volume, and we'll add up their total number of nuclei and keep track of that in the newly fused cell. And the controllable parameters for that are the fusion rates, one for every different type of cell. Getting more exciting is phagocytosis, where cells can consume one another. And so any cell can have a vector of phagocytosis rates of phagocytosing or consuming other live cells. And in addition, you can have a dead phagocytosis rate, which would be your probability of eating or consuming a dead cell. And when that happens, the cells will consume, the eating cell will consume the eaten cell and acquire all of its volume and its contents to create a bigger cell. And the built-in volume regulation in PhysiCell will eventually reduce the eating cell, the eater cell, back down to its original volume. And so that will kind of happen over time. Key parameters then are your rate of phagocytosing dead cells and your rates of phagocytosing the individual live cell types. Effector attack is one that's of interest to many of us in this room because we like to do immunotherapy. But we model this in kind of a hybrid way based upon surveying the literature and biological hypotheses that a cell I can attack a cell J. And the way we decide if that attack occurs, it weights a couple of factors together. That, first of all, I have a rate that I want to attack cells. So that's this RAI. This is a rate I want to attack that specific cell type. So let's say I have a CD8 T cell and he really wants to attack cancer cells and really does not want to attack macrophages. So if I'm in contact with a macrophage, this rate is maybe 0. Whereas if I'm in contact with a tumor cell, this rate may be higher, that I want to attack a cancer cell. But that attack may or may not be successful, depending upon the immunogenicity of the target cell. So I have the attacker cell has a property that modulates the attempt to attack. I have also an immunogenicity of the target cell just to help modulate whether that attack is successful. And if they're both high, then in my delta T, I have a higher probability of attacking that cell. And if I do attack that cell, then I'm going to increase the damage of that target cell. Now, the interesting thing is this is for individual pairwise interactions, which means that if you have multiple cells attacking a target at the same time, they're all adding to the damage of that target cell, and it can accumulate damage more quickly. It's up to the modeler, though, to say what to do with that damage. Maybe the cell repairs itself. Maybe it undergoes a mutation. Maybe it turns into Thanos. We don't know. But what we need to do is add an additional hypothesis, typically saying that damage increases apoptotic death in that cell. And so the key parameters in modulating effector attack are the attack rates, saying for all the different live cell types in this simulation, what are my rates of attacking those different cell types? Usually they will all be zeros, but you'll set a few of them to non-zero values. And then on the flip side, every cell would say, how immunogenic am I to the individual types? And so typically we'd set those to a non-zero value and equal, but maybe a cell over time evolves the ability to evade attack. And so you might want to do that. And the last thing is saying is how quickly can my cell damage things when I do attack it? So you can imagine exhausted T cells, for example, might have a very low damage rate, that maybe they're not very good at damaging cells anymore. There are many possibilities you can model with this kind of formulation. And so drawing upon all these different built-in process or behavior models, each of them with well-defined parameters in the reference implementations, allows to create a variety of signals in the behavior dictionary. And so one thing I will distribute a supplementary material after this talk is our current list of available signals. It's a supplementary paper to a preprint we're writing right now. So I will just put this into the GitHub repository so we can have access to the current list of available symbols. But we have all these available behaviors with human readable names like oxygen secretion or cycle entry or apoptosis or migration speed or cell-cell adhesion, for example, or attack cancer cell, fuse to epithelial cell. All of these are uniquely addressable names that map onto specific parameters in these reference models. So we have the beginning of an ontology and of a controlled vocabulary. And if you are going to be working in C++, we have an API that simplifies referring to these things. You could say that for any one of these behaviors, you take a cell and go to its pointer, and you say, for this cell, I want to modulate the following behavior, say cycle entry. So this is something in my dictionary. And then I want to say, set the value to this value. And that's it. That's the syntax for every possible built-in model in PhysiCell without having to learn a whole bunch of syntax for classes. So for example, for some cell with a pointer, I'm going to set cycle entry rate to 0.001 minutes inverse. That's it. Or if I want to say, I want to start phagocytosing dead cells, I could say for my cell, set phagocytosis dead cell to 0.01. And we've got that. The other thing you can do is you can access reference values from your cell line. And so if you need to get properties of kind of like reference values, say, here's my value in the absence of any signals, and then here's kind of where I want to change it to, and that can be helpful too. Signals are actually even easier. So we have a number of families of signals, things like oxygen or intracellular oxygen or oxygen gradient, pressure, volume, contact with different cell types, maybe how damaged I am from a vector attack, or whether I'm dead or alive, or apoptotic or necrotic. So I have a variety of signal names available in plain English, and I can query them at my cell's location and use them as inputs to model rules. And so we have an API that makes that very easy too. So for some cell, get single signal and the name of the signal, and that's it. And everything else has been abstracted. So you don't have to worry about a complex signal syntax to go and find the right class and method to say, how do I get my oxygen concentration in this box where I'm sitting? The biologist user or the modeler user shouldn't have to know all of that stuff. That's the infrastructure. What you want to know is how to turn it into a model. So examples might be, say, get single signal at my location, oxygen. Get single signal, pressure. Get single signal, how many melanocytes am I in contact with? And for us, that's just a unified API that you use in C++-based rules to do it. But now that we have a way to kind of unify our access of the signals and the behaviors, now we're in a place where we can actually build a language around it and not require us to write a C++ anymore. And so that's what we're teaching actually this year for the first time in the workshop. And so we have a grammar that goes like this. For some cell type T, a signal, so this is cell type T, something that's in my simulation or in my framework. Some signal S, this is something that's in my signal dictionary, one of the human readable symbols, increases or decreases some behavior B, this is a behavioral symbol in my behavior dictionary, and then optional arguments. So examples are for M0 macrophages, necrotic debris, cell debris, increases transformation to M1 macrophage. So this is a grammatical statement. Here's my cell type, M0 macrophages, that's my T. Here is my signal, necrotic cell debris, like in extracellular space. Here's the direction of the change. It increases some behavior. And here's my behavioral symbol, transformation to M1 macrophage. So you're coming into contact with necrotic or pro-inflammatory debris, and it starts turning into a pro-inflammatory M1-like macrophage. So there's, something can be written in this language. Or for malignant epithelial cells, doxorubicin increases apoptosis. So here's my cell type T. Here's my signal dictionary, extracellular doxorubicin. Here is my behavior B in my behavior dictionary. And this grammar connects them together into a hypothesis statement that we want to turn into a rule. So now in PhysiCell, we have developed an automated mapping to turn these rules into mathematics and then into code without having to actually write the math in the code. So we can focus most of our attention on coming up with the hypotheses. And so we use response functions, and this is basically any monotonically increasing function that goes between 0 or minimal response up to a maximum of 1 or maximum response. And it has to do so kind of smoothly, right? That as you get closer and closer to 1 towards your maximum response, it should taper off. So it should basically have a sigmoidal look, would be the best thing you can do. And so if we have this response function, then we can modulate a behavior starting at its base value, P naught, in the absence of signals, towards its maximum response value, PM, or saturated response value. And you can think of it as a linear interpolation, but with this non-linear response variable. So you get kind of a nice sigmoidal curve starting at P naught and increasing and saturating at P max. And it kind of has a familiar form that many of you are already using in your models. And for our response models, we tend to use Hill response functions. And this has a nice property that it doesn't take many parameters to describe. And it is very consistent with a lot of pharmacodynamics out there, and also with a lot of systems biology models. And so the idea, right, is that my signal is my input value. When my signal reaches my half of maximum response value, S over S half, these two terms are equal, and this ends up being a response of 1/2. So S half is a value where you reach half of your maximum response. I'm halfway between 0 and 1. And notice that as S goes to infinity, this tapers off towards 1. So it has a nice smooth function that says that at some point you can dump infinite signal into the system and it's not going to make a difference. You've run against your physical constraints. Something else is limiting you. So let me give an example. Oxygen increases cycle entry. So here's kind of the base behavioral statement, and then the optional argument saying from a minimum value, from a base value towards a maximum value, with a Hill response function with half max of 21.5 millimeters of partial pressure of oxygen, it's like 5% oxygen, and a Hill power of 4. You put these things together, and it would generate this mathematical response curve, where you start off at a very low division rate or cycle entry rate, and then as you get towards increasing oxygen towards your half max, you've reached halfway between the minimum and the maximum value. And then as your oxygen increases, eventually you're going to saturate towards your maximum value of this particular cycle entry rate of 0.042 hours inverse. And so this is a kind of a typical response curve that shows you how plain English statement like this maps onto mathematics very easily. And from there, if you have consistent mathematics, we can write this inside PhysiCell as auto-generating the response curve and modulating the parameter value, and you don't have to write that code. The interesting thing is now we have actually generalized this to become a multivariate response function. And so if you can add on multiple rules, so if I have multiple up signals, say 3 or 4 different growth factors that can all individually increase my cycle entry rate, for now we're going to go with the simplest possible assumption that they all can act, as a big OR operator, basically. We know that's not always right, but it's our starting point until we know otherwise. And so we can say that we can add up those signals in a multivariate version of a Hill response function. And the neat thing is adding a new term doesn't break your old terms. Each one of the old terms is regulated by their own individual half maxes. So they're kind of auto scaling in this way. And so if I want to add a new signal, a new rule to this model, it doesn't really hurt the old terms. So I can integrate old rules and new rules very easily this way. The other thing that's quite nice is that if you are in one of the specialized cases where most of the signals are 0, you go back to your original rule. So this multivariate form recovers the individual rules if all the signals but 1 are 0, but it does allow them to kind of combine and work together. So we come up with our multivariate version of the total up response for up rules. We come up with a total down response for our total down rules, and then we do a bilinear interpolation to integrate these competing signals, these up and down rules. So as an example, here's a typical model we've done where, for example, mechanical pressure is decreasing cycle entry. So you can see that for low mechanical pressure, you're up here along a single response curve. And as pressure increases, you're shutting down cycle entry pretty much everywhere. Then on the other axis, we have oxygen. That oxygen increases cycle entry rate. So notice that as you go and increase oxygen, especially when there's no pressure, you get kind of a classical response curve of oxygen increasing cycle entry until you saturate. But now you can put these two rules together in this automated way that basically you can say, how much cycling would I do if not for the down regulators? And then the down regulators further modulate you down this curve here. And so you can put these two responses together in a nice, consistent and automated way, and it's a starting point. Now that we have a grammar and an automated way to turn it into mathematics, now that opens up the possibility of building graphical editing tools, which Randy Highland has done heroic work in turning into a model editor. And so that's what actually we'll start with in the next session, is you can now say, well, I have a cell type, a signal, a behavior that I'm modulating, and a direction of the modulation. That is what I need to write a rule. And so we can add a rule to a table, save it off to a file, and then PhysiCell will parse that rule and turn it into the code on the fly when you run your model. So you won't have to write any C++ for this. And the other neat thing about that is that this will auto-generate documentation as you go. Because you're not handwriting code, all of your hypotheses are the rules. And those rules are your model. And so now what we have done is PhysiCell will generate an HTML file that lists all of your hypotheses used to generate your modeling result and spit them out in your output directory as you run. And so we think that this would be good practice for future models, that you should include this auto-generated list in your methods section. Say, here are the model rules for my particular model, either in the detailed form with all the parameter values, or in a simplified form that just says auction increases cycle entry, and just basically the beginning parts of all these models. And so we think that that is a good practice for reproducibility. So to give an example, this is a model that we worked on with Lisa Cousins, Joe Gray, Laura Heiser, and Yang Huang Cheng at Oregon Health and Science University. And so Laura and Lisa in particular and Yang helped us come up with some model rules that we wrote in this grammar. And so our model rules are actually pretty simple. We start off with a tumor that auction increases cycle entry, pressure decreases cycle entry, so very classical mechanobiology here. The oxygen decreases necrosis, and oxygen and damage increases cell death, damage from effector attack. We'll get to that in a minute. And that dead cells release some debris, and that interferon gamma can change cell migration, decrease it. So there's our base tumor model. And then we add some macrophages. Start off with naive macrophages that contact with the dead cell will turn a naive macrophage into an M1 macrophage by increasing its transformation rate. That M0 macrophages, when they come into contact with dead cells, will decrease their migration speed because they kind of found something. They want to just linger there. And that dead cells are also going to be secreting debris because these cells could also die. M1 macrophages are now basically pro-inflammatory activated macrophages. And so they are going to come into contact with dead cells and also kind of stop and linger and do their thing, in particular phagocytosing dead cells. They will, the oxygen can, that in the present way to read this is that in low oxygen, they might be turning into tumor-associated macrophages or M2 macrophages. And that the reverse of that is that high oxygen would prevent that transformation. Interferon gamma is increasing cycle entry so that M1 macrophages start giving birth to more M1 macrophages in the tumor environment. That interferon gamma as our pro-inflammatory factors increasing phagocytosis. And these are doing things. And also M1 macrophages, not written here, are secreting pro-inflammatory factors, interferon gamma in particular. M2 macrophages are secreting an anti-inflammatory factor, in this case IL-10, and they are going to decrease migration still if they come into contact with things. But interferon gamma now is going to decrease their cycle entry. So these are primed to go negative regulatory. Interferon gamma increases their phagocytosis of dead cells, all of this. Then the fun thing is we started adding in the CD8 T cell rules. That anti-inflammatory factor will decrease the rate of naive T cells activating and becoming CD8 effector T cells. And interferon gamma, the pro-inflammatory factor, increases the rate of transformation. And that's pretty much, and then being dead increases debris secretion. So now you have a naive T cell that turns into an effector T cell, and they're going to be going and attacking tumor cells. And here, interferon gamma, pro-inflammatory factor, can cause them to cycle to give birth to more effector T cells, whereas the anti-inflammatory factor can decrease their attack activity and decrease their migration. And then contact with the tumor cells might decrease their migration speed. So say, hey, I found a target, I need to slow down. And that IL-10, the anti-inflammatory factor, would increase their rate of transformation to an exhausted T cell. And those are cells in our model, just T cells that don't do attack. And so a handful of fairly simple rules that in the olden days would have taken us quite a bit of time to handwrite in C++. But now we can use the rules editing format to generate machine readable rules that get parsed at runtime and automatically turned into model code. And you put these together and you get this. So let me pause this for a moment. So here we have a tumor with a ring of naive macrophages, that's the red ones, and naive T cells, these are the blue ones. And here are some just randomly placed tumor cells. The tumor is growing and it is getting a necrotic core, which means it's starting to release some dead debris. That dead debris is reaching macrophages, and some of them are going to activate into M1 macrophages, like this one over here, and a few activated macrophages over here. Now those become pro-inflammatory factors that are going to start activating naive T cells into CD8 effector T cells. See these magenta things around here. magenta cells, right? They're attacking tumor cells. So you're kind of seeing this nibbling away at the fringe of the tumor. But now we're starting to get, some of these macrophages are getting into hypoxic regions of the tumor, and they are starting to become anti-inflammatory macrophages, these green ones that are going to start transforming T cells into exhausted T cells. See these orange guys over here. So we see that these very simple rules, when you get down to it, I mean, it's to mathematicians, they look like complex rules. To biologists, they look like laughably simple rules. So probably the reality is somewhere in between. But a very small number of rules gives a cascade of behaviors that we know actually happens in cancer biology and in cancer immunology. That a tumor can initially be pro-inflammatory, and there can be initially a successful immune response. But we know that in many cancers, over time, particularly hypoxic tumors, will enrich for anti-inflammatory tumor-associated macrophages that stave off further immune surveillance and immune attack. And we see that whole cascade emerges from these rules as a consequence and did not have to be programmed in. And so that's kind of the crux of the signals and behaviors in PhysiCell, that we have this vocabulary of symbols of things in the environment, including contact with other cells, that a cell can sample to determine what's going on around it and uses the inputs of rules. And then the rules modulate specific behavioral parameters in our reference models, modulate things like cycle entry, apoptotic and necrotic death, migration parameters, secretion parameters, attack parameters, cell phagocytosis parameters, cell transformation parameters, and that you put these together into rules that should be intuitive, right? Drug increases death, that kind of thing. And then we can automatically turn those into model rules and start executing and exploring the models. And this is in fact what we're going to do in the next session. So future directions for the modeling language. Well, first of all, get the preprint out in the next 2 weeks or so. But we are going to be looking for other standardized models for things like symmetric and asymmetric division. I know that's of particular interest to a few of the participants here. Otherwise, there are some areas like, say, melanocytes, for example, use something called processes, which is not the same word I've been using, processes. This is a problem with biology, is that every word means something different in different realms of biology. But here, a process model means a thin cell extension that can extend mechanically over large distances to interact with another cell, to do things. This is very common in things like epithelial biology, where melanocytes will form processes to connect to epithelial cells fairly far away and deliver melanocytes to deal with UV damage. Or you can have, of course, neurons that extend out processes to either drive migration or to maybe drive connections between nerve cells to create lovely neural networks, which we tend to like in our brains. And so those are good. There are other areas like in kidney biology that also have processes. So finding ways to model that nicely could be another interesting thing to add as a standardized reference model in PhysiCell. We could certainly do more sophisticated response functions and add missing symbols. We know we're missing symbols like and or operators. Say maybe you need oxygen and glucose simultaneously to increase cycle entry rather than just one or the other alone. Or maybe a drug plus some other compound together makes a high response, but not the drug alone, not the other compound alone. Or you have factor A and factor B that can individually increase something, but maybe their product decreases something, that they interfere in some weird way. So these are kinds of symbols that we might want to add to the language in the future and accommodate. And we might want to add things like negation symbols. So right now we don't have a symbol for the word low. So we have to do some workarounds, as we'll see in the next session, to deal with things like hypoxia. But for a running start, we can do a lot of models this way, and that's what we hope to show and explore together in the coming week. So the next session after our break, we'll introduce PhysiCell Studio and also the cloud version. And in that, we're going to start building our very first models from the ground up. We're going to build a tumor growth model that has oxygen driving cell cycling and cell death. And cells are going to release debris and a couple other nice things. And then we're going to iteratively start adding up more features into this model over the coming session. And so that's the direction we're going to go here. We actually have quite a lot of time for questions here. So I'm very happy to stop here and give the break of extra break time. This is actually a little bit faster than I expected it to be. Are there any questions? Ashok.
Hi, Paul. Thanks. That was fascinating and really useful. Very exciting. I had a question about the functions which you use to define responses. It should be possible to go in and edit those, right? If we wanted to, for example, have the response described by something different.
So that's a really great question. Right now, we have primarily supported Hill response functions just because they have nice properties. The one thing you can control very easily right now is the half maxes and the Hill powers, and then the saturation values. We, in future versions, want to support in the language other response curves like capped linear, for example. But for the first version of language, we want to be careful not to bite off more than we can chew. Now, in this, if you write it in handwritten code, you can definitely write more complex response functions if you need them.
So we can get into the C++ code and change the function.
Yeah, you can go into C++, basically write
because
your own
we could imagine writing a function that incorporates an effective AND, for example, right, in that way.
Oh, we would definitely love to see that.
Like just multiplying two signals together, right? That's what.
Right. That would be like the classical AND signal, right?
Yeah, exactly. Yeah.
And so one thing we're thinking about adding to the language actually is an AND signal, AND symbol. Sorry. So it might be, for example, oxygen and I'm just going to make something up. Oxygen and IL-6. And for us would mean product, and then that could be the input to a Hill response function to increase something or decrease something. So actually, if we added the AND symbol to the language and added those permutations, then we could use the existing framework to get more complex interactions and synergies.
Absolutely, that would be definitely much more elegant. Yeah.
Okay.
But
yeah, we could totally do that pretty easily. But I'm trying to avoid the temptation of writing too much into the first version of the language.
Right.
But you're right, and you could have AND operations as signals, and then those could either increase or decrease the behaviors. The other thing we're going to be adding very soon, but only in version 2, because I'm trying to be disciplined for once, is that individual rules could have you push towards different saturating values. Right now, they basically go to the maximum with those values. But we found some cases now with in vitro data and in vivo data where you may want some growth factor 1 pushes you towards one value, growth factor 2 is more effective, pushes you to a higher value, and that you may want to have a variety of values. And we have an idea on how to generalize what we have right now to do that, but we didn't want to overcomplicate it in version 1. And we're looking for a little bit more. So we would love to work together with you on that, by the way. We would love your input on how to improve that.
Oh, great. Thanks. Yeah.
Oh, heavens. Thank you.
Thank you. Thank you.
Other questions? This is really fantastic. So yeah, what we're trying to do right now is just say, can we start migrating agent-based model development from writing C++ to writing these hypothesis statements? And let's see how far we can take it in version 1 of the language, and then identify what's missing and come back for a second pass and say, what was missing in version 1 language and can we add it on? The other thing is that there's really nothing here that couldn't also be implemented in other modeling frameworks. We would love this to become a unifying language to help different models cross-validate one another. And so if Chase wants to implement these reference behavior models, then the symbols would mean the same thing in both modeling frameworks. If PhysiCell 3D wanted to implement them, or Morpheus, or Tissue Simulation Toolkit, or BioCellian, that would be fantastic. For us, that's an ideal thing. It's not competition to us. It's a better community if our model frameworks can talk to each other. And so we're hoping that by just writing down what we mean by these behaviors with reference models, that we might have a starting point for trading things and trading models. That said, PhysiCell is the best. Please do everything in PhysiCell. But nonetheless, we would really love actually to see a little bit more compatibility between frameworks. Any other thoughts? I think we can go ahead and stop the recording now. And